There we go. So there are over 40,000 fMRI studies out there in the literature at the moment. And on average, these studies rely on very small samples to detect small effects. Coupled with strong publication biases, we're left with a very large, very underpowered literature, chock full of false positives. In order to make sense of such a literature, we need to synthesize results across many studies, and that's where meta-analytic frameworks come in. The two most popular meta-analytic frameworks at the moment are BrainMap and Neurosynth. BrainMap relies on manual annotation of fMRI studies according to a domain-specific taxonomy, the cognitive paradigm ontology. As a result of its very detail-oriented approach, BrainMap currently contains about 3,000 fMRI papers, and it's largely incapable of scaling with the growing literature. Neurosynth was developed to address this problem. It uses automated methods of curating and annotating fMRI articles, and namely bases annotations off of term frequencies in abstracts. As a result of this approach, it currently contains over 11,000 fMRI articles. In spite of its obvious appeal, though, Neurosynth's annotation procedure has not yet been quantitatively assessed, nor has the effect of the performance of this procedure been assessed in regards to meta-analyses. So what we've done is we have taken BrainMap's labels and applied Neurosynth's annotation procedure to evaluate the performance of Neurosynth's annotation procedure in order to answer the question, is Neurosynth's annotation method accurate enough, and is its database large enough to detect true effects in meta-analyses via a series of rudimentary simulated meta-analyses? So the first step in our procedure was to generate search terms for each of the cognitive paradigm ontology labels that were sufficiently represented in our corpus. So there were 69 of those. For example, for the label explicit memory, we would search explicit or declarative and memoir asterisk, which would return memory, memorization, etc. We then pulled the abstracts for our corpus from PubMed and transformed those abstracts into term frequencies using BrainMap or Neurosynth's in a vectorization procedure. We then applied our search terms to these term frequencies in order to predict CogPo labels, as well as to the full Neurosynth database in order to get the sample size associated with the search. We computed positive and negative predictive values as measures of annotation performance by comparing the manual annotations, which we use as the true labels, against the predicted labels from the searches. The next step in our simulations was to generate predicted confusion matrices. So these reflected the predicted number of true positive, false negative, and true negative studies when you apply the search term to the full Neurosynth database. So when you search Neurosynth for working memory, you get back a sample of n studies, and those studies will be a mix of studies that are actually about working memory and studies that are not about working memory. We tried to predict the number of each of those cells from the sample size and the annotation performance. We then used the confusion matrix to compute a predicted chi-square contingency table, reflecting the predicted number of studies that would have a focus in a region with a true effect. This was dependent on estimates of the experiment-wise power level across the literature. In this case, this refers to the proportion of studies that would actually find the peak of a cluster within 6 millimeters of this hypothetical true effect region. And we also included false positive rate from the literature. So once we had the chi-square contingency table, we performed chi-square tests to assess the significance of the meta-analysis. Because we were only simulating one voxel, we couldn't perform FDR correction like Neurosynth does. So instead of a threshold of p is less than 0.01 FDR corrected, we used p is less than 0.001 uncorrected. All right, so as an example, I'll walk you through working explicit memory. For the label explicit memory, we searched explicit or declarative and memoir asterisk, which returned a positive predictive value of That one's not me. Okay. A positive predictive value of 0.39, a negative predictive value of 0.91, and a sample size of 119 papers in the Neurosynth database. From this annotation performance and sample size, we generated our confusion matrix. And of the 119 studies in the sample, we predicted that about 46 of them would actually be about explicit memory. From the confusion matrix, we generated a contingency table, and with an experiment-wise power of 8% across the literature, which was our middle-of-the-road estimate, we would predict only about 4 of the 119 studies to actually have a focus within 6 millimeters of this hypothetical true effect voxel. So we performed a chi-square contingency table, or chi-square test on that, and got a p-value of 0.064, which according to our criteria would not be significant, indicating that that meta-analysis would not find a true effect if there is one. So by bootstrapping the BrainMap database 10,000 times, we were able to estimate the proportion of those meta-analyses that would be significant as an estimate of meta-analytic power associated with that label. And what we found was that with an experiment-wise power level of about 8%, over 2/3 of the labels in our corpus were sufficiently powered at the meta-analytic level, indicating that Neurosynth actually performs quite well, even when individual experiments have very low power. However, a number of labels that researchers are likely to be interested in, such as emotion induction or explicit memory, failed to perform. Now, in order to test our hypothesis that annotation performance is in fact associated with meta-analytic findings, we performed a separate analysis with real data. And what we did for this is we bootstrapped the Neurosynth database 1,000 times and applied our searches to the bootstrap databases. We then performed MKDA meta-analyses on those bootstrap samples. And for each pair of the bootstrapped meta-analyses, we took the posterior probability maps and performed Spearman correlation to get a distribution of Spearman correlations for a given search-based, for a given label. We use this as an estimate of the meta-analytic stability associated with the search term. We also repeated the procedure with the true labels, meaning the manual annotations, as well as the BrainMap database, as an estimate of the stability associated with the label itself. We fed these into a regression analysis, where the dependent variable was the mean Spearman from the Neurosynth meta-analyses, and the independent variables were the annotation performance, which for this we use the harmonic mean of the positive and negative predictive values, as well as the Neurosynth sample size and the mean Spearman from the BrainMap meta-analyses. What we found was that the annotation performance was significantly associated with meta-analytic stability above and beyond the effects of sample size and stability associated with the label itself at p is equal to 0.001. Up here you can see the annotation performance plotted against the residuals from the null model, and the relationship doesn't appear to be driven by any one of the different groups of labels or dimensions that we used for this. So, in conclusion, we found that annotation and performance is associated with meta-analytic stability, and that this annotation performance differs across labels. In low power situations where individual experiments have about between 3 to 8% power, Neurosynth may benefit from a more advanced annotation method, perhaps something like trained classifiers, or limiting itself to features of interest, such as an ontology of interest like the cognitive atlas. However, in a high power domain where power is about 20% or greater, over 80% of labels were sufficiently powered. So Neurosynth actually performed very well. Nevertheless, it is very difficult for can be very difficult for researchers to generate these search terms especially when they don't have access to the labels to compare against like we did. So we hope that we can move forward by giving Neurosynth the ability to predict constructs of interest rather than individual terms, allowing researchers to focus on the meta-analyses rather than choosing search terms of interest. All right. I would like to thank everyone in my lab, and thank you all for viewing this. If anyone's interested more, they can see my poster, which is number 1674, I believe. Yes.